Okay, so we're going to have a chat about Half-Life. And Half-Life, well, we're interested in Half-Life because the decay of any radioactive nucleus happens spontaneously. In other words, we can't predict when it's going to happen, and we can't find any factors that influence when that happens. And so half-life is a kind of statistical way of coping with that random spontaneous decay, because it turns out that if we have a large group of nuclei, the time it takes for half of them to decay is fixed for any isotope. Every isotope has its own half-life, so we can't know exactly which nuclei are going to decay, but we can know that after a certain amount of time, exactly half of them will have decayed. That means that the other thing that halves after one half-life is the number of particles coming out of the sample per second. It's like the activity of the sample halves, as well as the number of undecayed radioactive nuclei. So we're going to have a look at americium-241 as an example. That's what we use in smoke detectors. It's got a half-life of 432 years. And so we're going to graph up, and first of all use a graph and then use some equations to try and work out how long it might take for that americium-241 to drop below 10% of the original amount. And so we could do amounts in grams or micrograms or whatever of americium, but sometimes it's nice on our Y scale. It can work quite well just to use things like percentages. So that way we start with 100%, 50%, 25, 12.5. Notice that the gap is halving each time, and along the bottom, instead of putting 432 years, it's nice just to put 1, 2, 3, 4, 5 half-lives. Just makes it easy to do your graph. And so then we know that after 0 time, we're going to have 100% of our sample, and after one half-life, half of them are going to have decayed. So we're down to 50%. After another half-life, half of that. After another half-life, half of that. And so what we notice is that although our line is getting closer and closer and closer to that time axis, it never actually touches it. We need to be really careful when we're drawing a curve to join those dots that our curve doesn't cross the time axis, because that would imply that the last nucleus has decayed. We're talking about a large group. When we've got a large group, you can keep halving it for an infinitely great number of halves and still have enough that you can halve it again. So we make an asymptote with the time axis like that. And if we're interested in 10%, that's a little bit below 12.5. So we can kind of go across from there and see that it's a little bit more than 3 half-lives just drawing off our graph. So a little bit more than about 1,300 years. But we can do this mathematically as well. The trick to doing it mathematically is to start by writing down an equation. And so we know that whatever we start off with is going to halve n times. So we're going to have that as a multiplier in our equation. We're going to start off with 100%. 100 times a half, n times, should give us 10%. And so we're going to start by rearranging that equation. 10 over 100. 10 over 100 is 0.5n, or the only way to solve this kind of equation is to hit it with logs. And remember that by doing that, hitting it with logs, it allows us to move the n from up the top to down in front of that log there. So we end up with a log of 0.1 over a log of 0.5, which gives us 3.32 half-lives. How long is that? 1,435 years.